Hello there, everyone. Welcome to episode number 677 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by yours truly, Amelia Dalton. In this week's podcast, we're stepping onto the frontier of battery innovation. My guest is Volexion CEO Joe Adiletta. Joe and I discuss why some battery materials perform great in the lab but fail in real-world production. What designing backward from the factory means in terms of battery design, and the role that manufacturing plays when it comes to the scaling of these kinds of advanced materials. Also this week, I check out a revolutionary new memristor that can function at a temperature around 1300 degrees Fahrenheit. But first, please welcome Joe to Fish Fry. Hi, Joe. Thank you so much for joining me.
It's a pleasure to be here. Thank you for having me.
Absolutely. Okay, so first off, tell my audience a bit about Volexion.
Yeah, so we're a coatings company, advanced materials and manufacturing that deals primarily with the battery industry. So, when you pick up your regular old Energizer Duracell battery off the shelf, you got a pointy end, you got a flat end. And that's the positive side. And the negative side, the positive side is called the cathode end of the battery. The negative is the anode. And each of these sides is really governed by a very bespoke powder that gets used in manufacturing that does all the heavy lifting inside the battery, right? Makes the electrons and the ions flow back and forth. So we take the cathode active material powder and we coat it with a thin layer of graphene material. So really, we do two things. We make a low-cost, high-performance graphene material, and we coat things with it pretty simply.
Very cool. All right, so let's talk a little bit about the intersection of battery manufacturing and advanced materials. So, Joe, why do you think that some battery materials perform great in a lab but fail in real-world production?
Yeah, that's a really great question. The fundamental reality of batteries is that there are so many requirements that these things have to make. Battery luminary Yetming Chang, professor at MIT, who's a founder of half a dozen or more different companies, used to tell customers and other employees that it's not really the 19 out of 20 requirements that batteries do meet. It's the one that they don't that kind of gets you not qualified for any given application. So they fail for a number of reasons, right? But as a startup or early stage company, not everybody knows what all of these requirements actually look like, right? So you can chalk that up maybe to a little bit of lack of experience or industrial knowledge. Not all of these things can be tested at the end of the day. Like literally startups like ours have distinct analytical capability gaps that are very, very expensive and time consuming to fill. Right. And not all of these requirements are necessarily evident at a small scale, right? The easiest description there is perhaps safety testing, right? If you test teeny little batteries, they don't tend to do bad things. But as you build bigger and bigger batteries and put more and more energy into confined spaces, things can get hairy. So you might not know that, right, for some period of time. So requirements, testing, scale, all different contributors to why you might find something really great in the lab, but that it might fail in real world production.
That makes sense. So recently I heard a term designing backward from the factory. So talk to me about what this means and why it has become a requirement for survival these days.
Yeah, I mean, like I said earlier, batteries are incredibly complex electromechanical systems, right? That are mechanically put together with very, very high tolerances. So you really have to understand how these things are getting made at the end of the day, because working backwards, if you have to materially change any of the processes that are used to make these things, it can go really wrong and go really sideways and be very costly really, really, really quickly, right? An old battery used to tell me that batteries, the battery industry is the only one where you manufacture things like baklava, right? And do that successfully. It's like layer after layer after layer in a confined space. And if you've ever done any bit of baking, right, you think about what it takes to take a recipe and even bake something like baklava successfully. Now think about the increasingly high manufacturing tolerances and capital involved in the scale of the battery industry. And it gets really complex really fast.
Let's talk about scaling. Now, that is a critical element here. So, what role do you see manufacturing playing when it comes to scaling these kinds of materials?
Yeah, ultimately, the simplest way to say it is scale is the product, right? You have to be able to make batteries at billions of cells. I mean, if you look around just your desk, I'm looking around mine right now, right? I've got an iPhone, I've got some AirPods, I've got a wireless keyboard and mouse, I've got my laptop, right? I'm surrounded by at least half a dozen lithium ion batteries just here, right? And you multiply that by the number of people globally, there are billions and billions of devices out there. And so you have to do this at incredibly high quality. And certainly, over time you hear about recalls or fires or this and that, but the level of defects and precision involved here is really exceptional at the end of the day. So you have to think about things in terms of scale, and that scale ultimately being the product itself.
All right. So, what kind of applications do you guys see taking advantage of your groundbreaking technology, and where are you guys headed in the future?
That's really the beauty of what we do is we're platform technology that's applicable across the board, both to state-of-the-art technologies today as well as those that are on the roadmap and emerging in the future, right? So you want a thinner iPhone? Great, we can help with that. You want to drive further? Done. You want more resilience on the grid and backup power? We can help with that. Want to put your drone in the air more quickly, it's great. We can do that too. So really, again, the beauty of what we do is it's a platform both electrochemically and on an applications type basis.
So, Joe, where is Volexion headed in the future?
That's a great question. So remember, we do two things, right? We make a low cost, high performance graphene material and we coat things with it. The reality is that graphene is like the world's great interfacial modifier, chemically, electrically, thermally, mechanically. So we are more broadly on the hunt for complex, high value interfaces to modify and make better.
Fantastic. All right, Joe, it is time for your off the cuff question. So, if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
Oh, one meal. That's a great question. Well, I'm going to say I cook, this is fish fry, right? Reminds me of, soul food, Southern cooking. I make a great gumbo. It takes me, the better part of the day to make it. And the beauty of that is it's our tradition here with my family. I've got 4 kids. We do that on back to school night every year. So I've been doing it probably for the last half dozen years. And it seems to get better every year, but it's really, a tradition that brings together family and, the thoughts and goals and desires for a new year. So it's almost like a different New Year's Eve tradition for us that's just on back to school night. So I love doing that every year and I wouldn't trade that for it.
I love it. That sounds wonderful. Well, Joe, I think that's all I have time for today. Thank you so much for joining me.
Wonderful being here with you. Thanks again for having me.
Have you heard about the new heat-proof memory device? All right, so get this. A team of researchers at the University of Southern California recently unveiled a new type of memory device that can continue to operate without failure at 700 degrees Celsius, or around 1300 degrees Fahrenheit. And yes, if your reaction is, whoa, that is completely valid because this temperature exceeds molten lava and goes way beyond anything previously achieved for this class of technology. And actually, it might be able to go beyond 700 degrees because 700 was simply the maximum their equipment could test. So, this type of technology that can withstand this crazy amount of heat is a memristor. Jian Zhao, the study's first author, built the device using tungsten for the top electrode, hafnium oxide ceramic in the middle, and graphene for the bottom layer. Tungsten in particular was used because it has the highest melting point of any element, while graphene was also used for its exceptional strength and heat resistance. And from this combination came some crazy performance. This device was able to retain data for more than 50 hours at 700 degrees without needing to be refreshed. Operating at just 1.5 volts, this component was also able to sustain over 1 billion switching cycles at this super high temperature, and was able to achieve speeds measured in tens of nanoseconds. And possibly the best part of the story, or at least my favorite part, was that this discovery was not planned. Joshua Yang, who led this USC research team, says, "To be honest, it was by accident, as most discoveries are. If you can predict it, it's usually not surprising, and probably not significant enough." Okay, so let's back up a second. In conventional electronics, we all know, heat causes metal atoms in the top electrode to slowly migrate through the ceramic layer. Eventually, they reach the bottom electrode, creating a permanent connection that short circuits the device and leaves it stuck in an on state. So what makes this device different? Well, first, graphene prevents this failure. And when you combine graphene with tungsten, then the magic really happens. Yang actually describes this combination of graphene and tungsten as being similar to oil and water. Tungsten atoms that approach the graphene surface cannot attach to it. Without a stable point to settle, they drift away instead of forming a conductive bridge. This prevents short circuits and preserves the device's function even under extreme heat. And the researchers confirmed this mechanism works using a variety of different methods, including advanced electron microscopy, spectroscopy, and quantum level simulations. So, an unexpected result when they were originally attempting to create a different graphene-based device has turned into a foundational principle. And even further, this approach could help researchers identify other materials with similar surface characteristics, which could also mean that scalability for these kinds of devices could be a reality at some point. Okay, so what kind of applications would these types of devices be a good fit for? All right, everyone at once. Space! Yes, the goal for space exploration electronics is 500 degrees Celsius. Take Venus, for example. It has a surface temperature around that level, and every lander we've sent up there so far has failed due to the extreme heat. But it's not just space applications that could take advantage of this ability to function under extreme heat. They could also be used in geothermal energy systems, which require electronics to function deep underground, where surrounding rock can glow red hot. And also nuclear and fusion systems, which expose equipment to intense heat. Even in everyday settings, durability improves significantly. A device rated for 700 degrees could be extremely robust for automotive systems, for instance. And then there's AI. Joshua Yang explains the benefits of this type of technology in AI systems like this. Over 92% of the computing in AI systems like ChatGPT is nothing but matrix multiplication. This type of device can perform that in the most efficient way, orders of magnitude faster and at lower energy. So where is this technology headed from here? Well, Joshua Yang and 3 co-authors of this study have co-founded a company called TetraMem to commercialize memristor-based AI chips at room temperature. Their lab is already using working chips from TetraMem for machine learning tasks. And the high temperature version at the center of this research could extend those capabilities to environments where traditional electronics can't function, which would allow devices such as spacecraft or industrial sensors to process data directly on site. So, are these memristors ready for prime time? Nope. But as Joshua Yang points out, this is the first step. It's still a long way to go. But logically, you can see now it makes it possible. The missing component has been made. Also noting, space exploration has never been so real, so close, and at such a large scale. This paper represents a critical leap into a much larger, more exciting frontier. And I couldn't agree more. Well, folks, if you'd like even more information about this study or more information about Volexion, I've included a couple links below the player on this week's Fish Fryin' page on eejournal.com. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If LinkedIn is your thing, I dig it. You can follow me or us on LinkedIn. And we are also on Blue Sky Social and Mastodon too. And we have a YouTube channel, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me. And of course, you can subscribe to our EE Journal YouTube channel as well. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of April 17th, 2026, I'm Amelia Dalton, and you've been fried.